Hey, AP Physics, see it's Horner, and we're looking at 1990 M1. So this is Mechanics 1. We have an object of a mass moving along the x-axis with a velocity, so notice that it is going right. And it is slowed by a frictional force that has a value of negative kV, where k is a constant. And at time 0, the object has a velocity v0 at position x equals 0 shown above. So we know that it's moving and it's got some sort of speed. They want us to find what is the initial acceleration. They want both magnitude and direction produced by the resistive force. So first thing I would do is do just a really quick free body diagram. We know that going to the right is some sort of force, and there's got to be a force going to the right because this is traveling with a velocity. The force to the left is going to be negative kV. Straight down is mg, and straight up is going to be the normal force. Because the normal force and mg are the same because it's on a flat plane, we really can just ignore the n and we can ignore the mg, obviously. So no big deal there. To find this initial acceleration, we're going to do the sum of the forces in the x direction should be equal to the mass times the acceleration in that x direction. The only thing that we have going is the one going to the left. So this is negative kV, and that's equal to ma. So now at this point, all you have to do is just solve for a. So a here would be equal to negative k v naught all over m. This v naught is pretty important because it says it has an object velocity of v naught. So that right there, believe it or not, is 3 points. You get 1 point for this, 1 point for filling in what the F net is, and 1 point for rearranging it. So that really is not too bad. Let's go on and look at the next part. The next part says it wants us to derive an equation for the object's velocity as a function of time t, and sketch this function on the axis below. Let a velocity directed to the right be considered positive. So for this one, we know that acceleration is equal to dv over dt. So that's just the definition for acceleration. We know that for this one, dv over dt, from what we did before, is equal to negative kv all over m. And if we want to, we could say that we could go through and just say dv over v is equal to negative k over m dt. So the question is, what did we do there? Basically, all we did is we changed the dt, we swapped places with the v, and when you do that, you get dv over v is equal to negative k over m. So the problem here, and the reason why we did this, is we're ready to integrate. But because a lot of you have not had integration or you're just in the beginning stages, we're going to stop here. If that bothers you, I'm really sorry. But I can tell you that this part of the problem is worth, there are 6 points to this part of the problem. And right now, if you don't integrate and all you do is just write this down, you get 1 point. And then if you write this down, you get 1 point. The rest of it is through integration and drawing the curve. So my question for you is, could you draw the curve? Do you really kind of know what's already happening here? And the interesting thing is, yeah, you probably do know that if this thing is traveling to the right and there is a force of friction on it, it's just like if you push off on a skateboard and then let go, there's not a constant force anymore. So really what would happen is you would have a asymptote or a curve that would come down like this, and it would approach that t and then would kind of level off. So that's really what that curve would look like. If you could guess on that one and get it right, you'd be fine. If not, that's okay too. But you actually get three points for that. The reason that it does have this exponential curve is because of the calculus and the integral there. So really, we'd probably get 3 out of 3 for this part. But really, that's it. That's all we can do on this one. So anyway, we're going to stop there and go on to part C. Part C. The problem with Part C is, guess what? Yes, it does. It kind of follows off of Part B, so we're not going to get any points for it either at this point. But this is definitely a problem that we're going to have to come back and look at one more time, since we need to talk a little bit about integration, but we want to wait till everybody's at a point where they can do this pretty comfortably.